So hello everyone. Today we are going to present our project, which is generative model using S4 architecture. First, about how we come up with this project. Please look at this table. Look at this performance, and you are gonna know that the S4 architecture is outperformed very many traditional architectures, including transformers, etc., etc. Because S4 is good at long-range dependencies. Therefore, we believe that S4 can be very good at image generation. So we want to combine some traditional generative models such as GANs and VAE with S4 to generate images with higher quality. So about our project goal. We first plan to implement a DC GAN, which is a very classic GAN architecture. We plan to train it on a MNIST dataset and CIFAR dataset, and use the images it generated as our baseline. And then we're gonna combine S4 architectures with GAN and VAE, and compare the images generated by our improved architecture with DC GAN output. We believe that the fit score could be a good evaluation matrix to analyze the performance.
Coming to the background of state-space models, the state-space model is defined by these simple equations which are seen here. So it maps a 1D input signal to an n-dimensional latent space and then maps it back to a one-dimensional input space. So you can think of this as a linear RNN, where at every time step, you do some transition to hidden state and then add it to the input. That is shown in the first equation, that is x dot equal to ax plus bu. And then you get the output to a single dimension, and you can view the D of U as a skip connection where you add the input to the skip, and that becomes a skip connection. But for random parameters of A, B, C, and D, the model doesn't perform really well. Hence, there is hence there comes the hypomatrices. So, which is a certain set of matrices, and it is proven that it is really good with long range dependencies. And also, you can train an S4 model similar to a CNN, and then operate it and then use it as an RNN during inference. This massively improves the time of inferencing. So it is very well known that continuous representations work very well with audio waveforms and images.
Yeah, coming to the evaluation metric that we want to use, we plan to use the fetch at inception distance, or the FID score. So this is a metric that is most commonly used to evaluate the quality of the images generated by the image generation models. The way it works is that it measures the similarity between two sets of images. One is real and the other is generated images. The features are extracted from both these real and generated image sets from an intermediate layer of a pre-trained inception network. Using these feature networks, using these feature vectors, their respective Gaussian distributions are built, and the Wasserstein to distance between these two Gaussian distributions is the FID. So intuitively, if we think about it, the closer the two Gaussian distributions are, the better the quality of the images generated are. So the lower the FID score, the better is the quality of the images that are generated.
So we have set our baselines to be, we have first worked on DCGAN, and that became our baseline. So DCGAN is a deep convolutional generative adversarial network. So you can see that in the generator architecture, there are 4 convolution layers, and even in the discriminator architecture, there are 4 convolution layers. So the input to the generator is a noise, which then goes on to each and every convolution layer and outputs an image. And the generated image is then passed on to the discriminator along with the real image, and it generates a loss which is then used to train the parameters of all the convolution layers.
First, we tried to combine S4 architecture with GAN architecture and tried it on MNIST dataset. But unfortunately, this doesn't work very well. We tried several architectures. The first we tried is the generator is composed of an encoder and a bunch of S4 layers and then a decoder. First, we try to input the whole latent space to S4 layers, hope it can memory some meaningful information. But as you can see, the output is all gray and contain no meaningful information. And the generator and look at the generator and discriminator losses plot. And you're gonna find that discriminator is way more confident than before. And then we try to input columns of pixel values as for layers. We hope it can generate meaningful information based on the previous pixel value. But as you can see, it's not quite work as well. And the loss remains constant. So we come up with some potential causes of this failure. First, we guess we did not implement the correct architecture of the generator. This may be our future direction. Second is about that the generator takes noise as input. However, S4 cannot generate meaningful images from this random noise. And the last, we think that it may be our loss function issue because we just use a very classic binary Crosby entropy loss.
Yeah, so because the S4 GANs did not work very well, and because of the reason that S4 cannot memorize or make meaningful generation only by providing noise, we pivoted to a VAE architecture, which is the variational autoencoder architecture. So this is a typical VAE architecture, but in the encoder, instead of a linear layer or a convolutional layer, we replaced it with the S4 layers, as explained before. And similar to VA, we map it to a latent space which has its own mean and covariance of the distribution. And we then use the S4 layer as a decoder to decode from this distribution the image generation. The hyperparameters used are shown over here. We kept the loss function the same as before. We kept a relatively low batch size, and we increased the number of epochs to 30 for CIFAR and only 10 epochs for MNIST. Although during training, we learned that the S4 layers learned really fast when compared to other linear layers or convolutional layers. The number of S4 layers was kept to 2 in both the encoder and the decoder. These are the results that we got by running the S4 VAE. In the bottom part, you can see that the image is generated for the MNIST dataset, and you can see the quality of the image is extremely high. The above one is the real image, and the bottom one is the generated image. Even for the CIFAR dataset, we can see that the quality of image generation is extremely high. Coming to the FID score, which is our evaluation metric, we see for the MNIST dataset, we see a 1/3 decrease in the FID score, which is really great. But the most impressive result is for the CIFAR 10, where we saw a stark decrease in the FID score, which makes DCGAN really bad for image generation on the CIFAR 10 dataset, but it makes S4 really good. This also aligns with our motivation and the theory where we prove that S4 is much better at remembering information because CIFAR has 3 different channels and has a lot more pixels than MNIST. Coming to the limitations and the future work, training the S4 VA was extremely resource intensive. It took 48 gigabytes of GPU memory, while we kept only a batch size of 32 and only used 2 layers of S4. We believe that increasing the batch size and increasing the number of layers especially would make the performance of the S4 VA much better. We also believe that S4 GAN will work because as we can see from S4 VA, the S4 layers has the capacity or it is able to generate images well. So I think once we can stabilize the training the S4 GAN should work well. We can also implement different metrics such as CMDD and inception scores to evaluate the performance of the model. And we can also train the model on bigger data sets like ImageNet, which we did not do because of time limitations. Thank you.